Hello again. So in the previous video we saw that we had gone up to test 9 and it worked, and now we are on test 10. So test 10 is still testing our start and end nodes, but this time we are testing for invalid entries where we should reject the input. So that includes things like F because it's outside our range of 5 nodes, and 3. So let's give it a go. So, wrong one again. So this is the same place from where we left off. So if I type in an F, we can see it shows a message box which says error occurred. Please enter a valid node within your given range. And if I enter a 3, the same message box appears. So that's wonderful. So we will only be allowed to enter the right thing, which is really good. So that's a pass. And now we've done the creating the graph checks, and we're moving on to testing our optimizations. So we are going to begin with Dijkstra on an undirected graph, and we want to check that the optimization actually works, the system does it correctly. So we want to check that the correct shortest path, distance, and alternative shortest paths are shown. Now the way I went about this was I created my own graphs, stole some from the textbook, which I will reference if I have used any from a textbook, and I performed the optimizations on them myself, or looked at the answers in the textbook, and I then passed the same graphs into the system, and I saw whether they matched the expected result I think should have happened. So we're going to do that. Now I've linked all the graphs at the very end of this table, and if we have a look for test number 11, we are using graph A with start and end nodes A and D. This is our expected result. If I have a look at what graph A looks like, this is what graph A looks like. You know what would make our lives easier? If I did this, then what we can do is we can have the graphs on one window and the test page on the other window. Apologies, it's a little bit slow. So, apologies. Almost there, sorry. So it should load. And if we take this back to here, so test number 11. Right, so let's pass this graph through the system. So it has 4 nodes, and remember we are testing Dijkstra on an undirected graph. So we have 4 nodes, and edge AB has a weight of 5, edge AC has a weight of 1, edge AD has a weight of 3, edge BC has a weight of 0, edge BD has a weight of 2, edge CD has a weight of 2. Just a quick note, edge BC has a weight of 0. You can see there's no direct connection between node B and node C, and the system says that if an edge doesn't exist, just enter its weight as 0. So then we have to enter our start nodes, which were A and D, doesn't matter lowercase or uppercase as we've seen before, and this is what we get. So we get for our graph with the following information, and it lists the edges, it lists the weights, it lists the start and end nodes. They have found that the shortest distance is 3. Well, is that expected? Let's have a look. So yeah, the shortest distance is 3. The shortest path is AD or ACD, so they've got AD, and the alternative shortest path is the other one, so ACD. So that's wonderful. So Dijkstra on an undirected graph has worked correctly with this graph, so we can pass this test. So the system works for any given graph. But what if the graph we pass in doesn't, have edges, or is broken, or isn't the expected graph that should work with Dijkstra on an undirected graph? This is where test 12 comes in. So we want to make sure our system can handle graphs which have no direct connection or path between them, such as graph B. So for an input of graph B with start and end nodes A and C, we should have a statement output saying no such path exists or could be found. So let's try it out. Let's return to the main menu. Let's click on here. We have 3 nodes. AB is 5, AC is 0, and BC is 0. And our start and end nodes are A and C. And we have found the path isn't reachable, no such path was found. So it has dealt with that very nicely, saying no such path exists or could be found. I think another key thing to point out, and this isn't in the testing table, but if I pass in the same graph, alright, and this time if I enter my start and end nodes as A and B, what happens? Because we can clearly see we can go from A to B with the shortest distance of 5. So shall we see what happens? Because we should expect that to be shown. And it does, which is good. So this wasn't in the testing document, but I think it was worth seeing whether it works. So that's good. We can have a pass here. Now test number 13. So we're assured that Dijkstra on an undirected graph functions for both graphs which we should expect and graphs which may not be expected. Now test number 13 is Dijkstra on a directed graph. Let me just, okay, we've been here for 6 minutes. So this, when we decide to do Dijkstra on a directed graph, we will be asked the direction between 2 edges, and I will illustrate that for you just now. Another key thing to point out, which I don't think I pointed out before, which I didn't, I'm very sorry. This should work for Dijkstra on a directed graph and Bellman-Ford, because Bellman-Ford also does the same thing. So let me just type in Bellman-Ford here, and let me explain to you what I mean. I'm really sorry that I hadn't mentioned this earlier. Should have really filled this out ideally earlier. So apologies if that causes any inconvenience. Oh, not this one. Let's have a look. Not this one either. Hold on. Right, okay. It's this one as well. So, what I'm talking about, if I explain it. When we decide to do Dijkstra on a directed graph or Bellman-Ford, so if I show you, we have to, it works on directed graphs. Okay, so directed graph, directed graph. Now, how do we check if our graph is directed? How do we check for directions and paths? The way we do this is we ask the user to input their edge in as normal. So if I go on Dijkstra on a directed graph, if I say we have 3 nodes, they'll enter their edge weights in as normal. They'll enter their start and end nodes in as normal. But then they are asked for every edge which doesn't have a weight of 0, for every existing edge, whether there is a path from node A to node B, from node A to node C, A to D, and then similarly B to A, B to C, and so on. Yeah, and if there is a path, we're going to enter 1 for a yes, and if there isn't, 0 for a no. That's how the system knows which directions are allowed for the graph. And the same is for Bellman-Ford. So that's how directed graphs work in the system. And we want to validate this input. Let me check the time. So yeah, under a minute left, so we will do that in the next video.